Hi everyone, this is Module 8 Study Questions. I'm at the library, so you'll probably see some lights in the background, but hopefully that won't be too distracting. I thought it'd be a cleaner whiteboard. So let's get started. You're going to start with number 1, and I want you to do that one on your own. It's just matching the terms to the definitions, so go ahead and do that. Pause the video. Number 2 says, if the speed of an object doubles, what happens to its kinetic energy? Okay, you're going to have to think about the equation. What's the equation for kinetic energy? So its kinetic energy equals 1/2 times the mass times the velocity squared. So if you're doubling the speed, you're doubling the velocity, and what happens? So your choices are the kinetic energy doubles, the kinetic energy stays the same, or the kinetic energy is halved, or the kinetic energy quadruples. So what happens is the kinetic energy actually quadruples. Just to show you, I put some numbers in here. So we have 0.5, let's say the mass is 3, and the velocity, there's no units obviously, and the velocity is 2. So I did this in my head, hopefully it's right. 2 squared is 4, and then you multiply that by 3 and divide that by 2, you get 6. So let's say I double the speed, so now it's 4. Okay, so this would be 16, and then multiply that by 3, that's 48, and then divide that by 2, multiplying it by 0.5 divides it by 2, so you get 24. And so you have 4 sixes can go into 24. So it's quadrupling it, it's multiplying it by 4 when you double the speed. Number 3, which of the following is an example of an object with elastic potential energy? A stretched spring, books on a shelf, a moving arrow, or a falling oyster? Okay, so it has to be something that can be stretched and then goes back to the same position, so that is going to be the spring. Number 4, which of the following is an example of electromagnetic energy? A speeding car, sunlight, falling stone, a stretched bowstring. Think about that for a minute, and the answer is sunlight. So sunlight is always going to be electromagnetic waves. Number 5, friction causes kinetic energy to be converted into what? Okay, think about when I rub my hands together. They're getting warmer. So friction causes kinetic energy to turn into thermal energy. Number 6, what is the energy stored in the bonds between atoms and molecules called? Kinetic energy, mechanical energy, chemical energy, or thermal energy. Well, it's not moving energy, it's not kinetic energy, it's not a machine, it's not mechanical energy, so it's chemical energy. When you eat foods, you get the chemical energy that's stored in the bonds of the molecules that are making up the food. Number 7, which of the following is an example of the conversion of gravitational potential energy to kinetic energy? Striking a match, kicking a soccer ball, a falling raindrop, or a gasoline-powered engine. So just look at my picture. You have gravitational potential energy. You put energy into something by raising it up off the ground, and as soon as it starts moving, it turns into kinetic energy. As soon as the gravitational pull pulls it down and it starts moving, it becomes kinetic energy. And so that's going to be anything that's falling, so a falling raindrop would fit into that category. Number 8, what does the law of conservation of energy state? Do you guys remember that? Think about it for a moment. It's on page 286, the law of conservation of energy. Energy cannot be created or destroyed. It can only be converted from one form to another form or transferred from one object to another object. So it's a lot like the conservation of mass, right? Except in this case, you can also have it transferred from one object to another. But you're not creating any, and you're not destroying any energy. Number 9, what is work? Is work the product of speed and force, the sum of power and force, the product of force and distance, or the sum of motion and force? Okay, sum is adding and product is multiplication. And so if you just think about the equation you're supposed to memorize, work equals force times distance. And so that's a product So your answer is going to be the product of force and distance. Number 10, which of the following is a unit of work? Is it measured in joules, watts, horsepowers, or newtons? So what's a force measured in? Newtons. And then the distance is measured in meters. And a newton meter equals a joule. So that's your answer. It's measured in joules. What's work measured in? Or sorry, what's power measured in? So power, number 11, power is equal to work divided by which of the following variables? So what's going to go here in our equation? Time, force, distance, or mechanical advantage. So power is work over time. And what's it measured in again? So your work is measured in joules, and your time is always measured in seconds, and joules per second equals a watt. So power is measured in watts. Number 12, how is the work output of a machine related to its work input? You have a choice A, work output is always less than the work input. Work output is always greater than the work input. Work output is about the same as work input, or work output is always 0. So think about this. There's a reason why the answer is correct. So you figure out your answer first. So your work input is actually always going to be less than your work output. This is going to be less. What you put in, sorry, did I say that right? The work output is going to be less than the work input. You're going to put in more work, you're going to get out less work. And the reason is because of friction. That's the reason. Okay, hopefully that makes sense. Number 13, what can you say about the output force of a machine with a mechanical advantage much larger than 1? So if you look at the equation, it'll help you think about the answer. You can choose from the output force is much less than its input force. The output force is much larger than its input force. The output force and the input force are about the same. The output force is in the same direction as the input force. So what does the mechanical advantage of greater than 1 mean? It means that the machine greatly increased the input force. Okay, so the output force will be much larger than the input force. And you can see that if we just put in numbers here, like let's put a 4 here and a 1 here. The input force is smaller, the output force is larger, and then you get a big number, a mechanical advantage that's greater than 1. So the answer for that is B, work output is always greater than work input. And if you get stuck on this, just think about the equation. You'll have the equations for the test written down in your notes. Number 14, what other type of simple machine can a screw be considered a type of? A lever, an inclined plane, a pulley, or a wedge. This is the same for an auger that's used to drill into the ground and pull out the dirt. Remember this page in your book? A screw is an inclined plane wrapped around a central axis. So the answer is inclined plane. Number 15, does a weightlifter do work on the weight bar as he lifts it over his head? So remember our equation, and you should have this written down for your test, that work equals force times distance, and put those little arrows under it to remind you that it's only work if they're both in the same direction. So if he's lifting the weight bar over his head, the weight bar is moving up, and the force that he's using with his hands, that he's giving the weight bar with his hands, is also going up. So they're in the same direction. So work is being done there. The second part of the question says, is work done on the weight bar as he stands still holding the weights over his head for 5 seconds? Okay, he's standing. Hold on. All right, he's standing. He's putting a force upwards on the weight bar. Is the weight bar moving at all? No, there's no distance. The weight bar is not covering any distance, and so there's actually no work being done in the second part of the question there. If I ever go too fast on these questions, remember you can pause the video and think about it, look things up in your textbook. You're basically studying for the test right now. Okay, number 16, a small meteoroid is approaching Earth. It has a mass of 120 kilograms and a speed of 20 kilometers per second. How much kinetic energy does the meteoroid have? And it gives you a hint here. 1 kilometer is equal to 1,000 meters. Why would that be? Okay, let's remember our equation is kinetic energy equals 1/2 times the mass times the velocity squared. Okay, we have to start with our knowns. So we have the mass equals 120 kilograms, and we have our velocity, which is 20.0 kilometers per second. We have a problem here because this should be in meters per second, and so we're going to have to do a conversion, and it gives you the hint that 1 kilometer is equal to 1,000 meters. All right, so we're going to take our velocity of kilometers over 1 times line, and then we're going to plug in our conversion factors. So our kilometers have to go on the bottom to cancel out. So 1 kilometer down here and 1,000 meters here, and that equals 20 times 1,000, which is 20,000 meters. Now we have something that we can plug into our equation here. Okay, I just looked at the book, and the answer is incorrect in the book. So don't go with the book's answer. Let's see if I can get you the right answer. So we're going to plug things in with our new number. So we're not going to use this one. We're going to use our meters per second. Okay, so we're going to use kinetic energy equals, we're going to just put 0.5. It's easier to input in your calculator and think about it. And then 120 for kilograms. And we're going to do meters per second. So it's actually 20,000 meters per second. And this is going to give us a huge number, and that because that's squared there. So you're going to do 20,000 times 20,000 times 120 times 0.5. I'm going to pause this and get my calculator out. Okay, so I put all this into my calculator, and this is the massive number that I got. This is right. The book is not right for some reason. There's a typo. So what would my units be for this? It's asking for kinetic energy, so energy is measured in joules. And this is how I got joules. So I had kilograms, and then I have times meters per second times meters per second because it's squared. And so what I can do is I can put it as second squared on the bottom, and a kilogram times a meter per second squared. You can even do it like this, a kilogram times a meter per second squared. This is a Newton, and a Newton meter is a joule, and so that's how my answer ended up with joules right here. When you're solving these problems, I want you to go through these steps. I want you to write your knowns first here. I want you to write your equation. I want you to show your work, and I want you to get your answer. It's even helpful if you box your answer, because a lot of these questions are 4-point questions, and that's how you get your points. Number 17, suppose a 200 kilogram building supply is lifted into the air to be placed onto a workstation. How much energy is needed to lift the supplies 3 meters into the air? So list your knowns first. So you have a mass here of 200.0 kilograms. Make sure that 0 doesn't mess you up. It's still just 200 kilograms. And then you have a height, and that should give you a little bit of a hint of which equation we're going to use here. So we're going to use the potential energy. Potential energy equals mass times gravity times height. And we know gravity, right? And so we have a mass and we have a height, and we can figure out the potential energy by plugging those numbers in. All right, so then you need to show your work. So you have your knowns, you have your equation, and then you're gonna plug in numbers into your equation. And so you have the 200 times the 9.8. This is the acceleration due to gravity, so it's in meters per second squared, and then times 3. And so you work that out and you get your answer. And your units go like this. You have kilograms times meters per second squared. This whole thing right here is a Newton times a meter, and a Newton meter is equal to a joule. So your answer is going to be in joules, and the book says 5,880 joules. Just check that with your calculator to make sure that's right. And that is going to be potential energy. Number 18, a machine has an efficiency of 75%. What happens to 75% of the work put into the machine, and what happens to the other 25%? So first, what happens to 75% of the work put into the machine? So 75% of that is going to be your work output. What's the other 25% going to be? Unfortunately, it's going to just be lost to friction. So for number 18, 75% of the work input becomes work output, while the other 25% of work input is lost to friction. Number 19, say you are cracking nuts with a nutcracker. For the first part, you apply an input force of 12.5 newtons to the nutcracker, while the output force is 50 newtons. What is the actual mechanical advantage of the nutcracker? So you have to remember that actual mechanical advantage is for force, and it's output over input. Remember that the ideal mechanical advantage starts with an I, so that's in over out. So we're going to do out over in, and it's going to be for force. Okay, so we can plug our numbers into our equation. So we have an output force of 50 newtons and an input force of 12.5 newtons. So the units cancel out, and our number is 4. So we're doing 50 divided by 12.5. That equals 4. So that means that the machine is giving a greater force, 4 times of what you're putting into it. The machine is doing that 4 times better. Part B, if the input distance of the nutcracker is 15 centimeters and the output distance is 3 centimeters, what is the ideal mechanical advantage of the nutcracker? So remember your equation for ideal mechanical advantage starts with an I, so it's going to be in over out. And this is distance that it's measuring. Okay, so it says 15 centimeters input. And it says 3 centimeters output. And your units cancel and you get a number. 15 divided by 3 is 5. Now look at this. The actual mechanical advantage is 4. And the ideal mechanical advantage is 5. The actual mechanical advantage is always going to be smaller because the actual mechanical advantage factors in friction, and friction takes some of the force, transfers it away, and the ideal mechanical advantage does not include friction, so it's going to be a little bit higher. Okay, number 20, you exert a force of 500 newtons to walk 4 meters up a flight of stairs in 4 seconds. How much power do you use? Okay, remember, power is work divided by time. Let's write our knowns down. And so we have a force of 500 newtons, and we have a distance of 4 meters, and we have a time of 4 seconds. We can't just plug that in there. So first we have to figure out what the work is. So we're going to need to use the equation for work. That equals force times distance. And we have both of those so that we can just do that. So that's going to be 500 newtons times 4 meters. That's a Newton meter. And so that's going to give us joules. So that's what, 2,000? 2,000 joules. Okay, I better check and make sure I'm doing my math. Okay, so in the book, they don't even multiply these out. What they do in the book is they just input this for this. So your equation would look like power equals force times distance. So we're going to just plug those in there. 500 newtons times 4 meters over your time, which is 4 seconds. So you're going to do Newton meters, which is joules, and seconds on the bottom, and joules per second is watts. So your answer is going to be in watts, and then you just do 500 times 4 divided by 4. Those actually cancel out, and you're left with 500 watts. 500 Newton meters, which is joules, 500 joules per second, which is watts. All right, that was the last problem. Remember that you need to write out, let's see, can you see that? Write out your equations in one spot, and then put the units for what you measure things in, and it's really going to help you fly through the tests and choose your equations. And remember to show all your steps of all your work to get all your points, and good luck to you.